Alright, so we're going to talk about efficiency of our algorithms here quickly and just kind of get a general sense of how this could work and not go too much in depth into the details. But there's really two types of things we're looking for in terms of algorithm efficiency. We could look at the space that our algorithm takes up, so that's the memory size, so how much memory are we using and how is that allocated, and that's one way we can do it. In general, though, that can be a hardware issue. You can get more RAM, you can get a faster processor. We can deal with that, and that gets, as technology gets better, the space and size is not as big of an issue. What is really can be an issue is time. So time is a little bit more constant in terms of our program run, and we can get more efficiencies in our code with our code analysis in terms of time. So we focus more on the time part of this as opposed to more of the hardware part of this as we look forward. And so what we do is we assume that all of our operations have some sort of time attached to them. So declaring some variable x has some constant time, we'll call it C1 attached to it. And then looking at y, making it equal to 4, has some constant time, we'll call it C2. And that might be a little bit different on each run depending on just what's running in the background, or things aren't exactly the same all the time, but on an order of magnitude, if it's 5 seconds one time, it might be 6 seconds again. It's not going to be 500 or 0.5. So we want to kind of, we're just getting order of magnitude estimates on our efficiency here. We have another time, and we have all these other times as we go through this, and our total time for our run is just the all constants added up, and we had some function of n, which doesn't make sense right now, which we call our kind of constant time. So that just takes some set amount of time. Again, it's going to be on order of magnitude the same for all of these runs as we were to go forward. Where it gets a little bit more interesting is if we take our array, which is numbers, which we could change in size. So this has 1, 2, 3, 4, 5, 6 items in it. It could have 600, it could have 6 billion. We want to think about how that would change our efficiency as we look at our code. So if we look down here at this one, at this method, right, we have our constant time. And again, we're looking at order of magnitudes here, but we have some constant time that we have that's the same as above, again on an order of magnitude estimate. And then we are looping through our array, right? So we're going to loop through numbers, and that's going to depend on the size or the length of numbers. And so what we have is our constant time for x, right? Some constant time for that, times n, because we're going to do that n times. So that C1 is added n times because we loop through there n times, where that is the length of our array. And so our time to run this algorithm is n times C1 plus the constant time. Now, where we start to get a little bit mathy is, let's say that we were to make this instead of 6, right, we make it 600 or 6,000 or 6 billion. Right, what turns out to dominate our function, and we talk a little bit about as things go to infinity, is this drop swell. Even if this is big, right, if this is 6 billion, this is going to be larger, and it's even going to be larger than this in terms of what really dominates our function behavior. And so as n goes to infinity, which we have some sort of idea of a limit, we have this thing called big O of n. Our order is n. We expect this to take n size. This is growing linearly with our value of n. And so if we look at the one above it, this is a constant of 1. So this is some constant time. We say it is an order of 1. This is linear. Basically, as it gets bigger, it grows by some linear factor. And this is an order of n. And this is called our big O notation. All right? And we can apply it to different things. As we start looking at loops within loops, we see what happens with our efficiency. So there's, again, our constant time. And then this is going to happen n times, that's our length, right? And then inside of that length, something that's happening C5 is happening n times as well. So every item in the array gets looped through again through the array. So it's n times C5 in terms of all of the time that we have add this together, right? And so what happens here is our function is C5n squared plus n plus our constant time. And again, as n goes to infinity, that term dominates, n squared. Let's say you put in a billion. Even though a billion is large, a billion squared is much larger, and that starts to dominate our behavior of our function. And so the order of this is going to be n squared, so big O of n squared, which is less efficient, right, is not as good as big O of n or big O of a constant. So this grows exponentially as we start to get large. All right, and then we can do things where we look at kind of how things get let's say we loop the array, but we're only looking at, we multiply our iterator by 2. So it'd be 1, and then 2, and then 4, and then 8, and then 16, so on and so forth. And so what we're really looking at is how many powers of 2 are in the array. That's how many times this is going to function. Right? So that is our logarithm. So really what we're looking at is our log base 2 for our length, which is what's here. Right? And that will give us how many times we're going to print something out. So this is our big O of log base 2 of n. And so if we put it all together and kind of look at how this works, right, we could have our n, which is basically our input size, is our independent variable, and then we have time that depends on the input size. And so if you have a constant, right, that's your order of 1, right, that's a constant value. It doesn't really matter how big n is, your output is just always going to be the same. So it's not dependent on how large your input is. You have some constant time. Right, then you have a linear, this is big O of n. As n gets larger, you get some linear relationship. And again, the slope of that line could be different, right? But it's an order of magnitude estimate of it's just going to go as you make it n larger, you get some constant change to it in terms of time. You could be exponential, right? So as you get, this is n to some power, big order of n could be n squared, n to the third, n to the fourth, n to the n. Just depends on how many times you loop through your algorithm. Right? We could also be logarithmic, and so this is our log base something of n, and that depends on how many times something would go into it, just like we had on the previous example. And so what we can see here is at the lower range, right, there's not a ton of difference, especially down in here, right, that these are all kind of the same, and you might even think, well, my exponential or logarithmic or whatever it is a better value, bang for my buck, than even the constant. But where things start to really make a difference is you get large values. So as things get large, like you imagine all the tweets in the world, you have lots of them, you start to get some large variations in the efficiency of your code.